My name is Eduardo Vasquez, and I will be talking about artificial gravity structure, the project I chose, and the analysis and the design of it. Objective. This is a preliminary study of an artificial gravity structure meant for the use of astronauts in low Earth orbit, which is where the International Space Station lies. What it is this pod rotates in giant circles, creating artificial gravity, 9.8 meters per second. Centrifugal force simulates gravity. The analysis will focus on thermal effects and the structure integrity due to the acceleration at its fatigue life. An emphasis will be on the section where the structure is more susceptible to failure due to heat or acceleration induced by the motion of the structure. We'll be focusing on these particular structures. It is more susceptible to failure, and ANSYS is quite good at simulating those. So multiple considerations both in design and materials will be explored to optimize the structure by reducing weight and increasing strength. Again, the main objective is to obtain and design structure that will not fail and is both lightweight and resilient. Motivation and background. The effects of zero gravity for astronauts could be detrimental, resulting in balance problems, visual disturbances, damage to the heart muscle, and bone loss. In 2016, NASA set out to further investigate these effects by sending out a twin to space for a record of 340 days. It was found that over time, reduced gravity causes redistribution of fluids and loss of bone and muscle mass, which can cause health problems, reduce oxygen absorption, which slows down the cardiovascular activity and reduces performance. Although studying the effects of radiation, heating, and the effects of acceleration and fatigue on structure is nothing novel, the application is. Optimizing and deciding what the best design is can make long-term space travel or prolonged periods of time in space without the harmful side effects. Geometry. The analysis on a 3D geometry. It was modeled in Fusion 360 and imported onto ANSYS. Although full-scale structure simulation would be ideal, it just isn't possible with a student license. The main structure highlighted in red was redesigned and various iterations led to the final design. This is the final design, and this is the final design of the structure that we were actually dissecting. So initially we had two loads, which meant only two of these truss structures were used. Eventually I ended up adding multiple structures to make sure the safety factor was met and it wasn't being overloaded. So we had failed geometry. There was various attempts to optimize the structure. We used MATLAB codes to help us optimize what a reasonable structure should be like. And here we have the first real examination of what the structure should be like. And we ran a whole bunch of structures running at 10 meters radius, with a radius of 10 meters all the way up to 50 meters, to see what the acceleration needed to be for it to be the omega needed to be for it to be 9.81 meters per second squared. We tried to compromise, and at the end we chose 15 meters as radians, and taking a further in-depth look at what were going to be what it would look like, we saw that it would do half a circle in a second, which is not ideal, but also doing a 50 meter radius is also not reasonable. So we try to compromise. Back here is one of the very first structures we try to implement. Failed miserably, as you can see. So multiple designs were tested, and although some of them did not fail, they did fail the fatigue test quite miserably. Here was one of the first serious designs we had, and when we analyzed it, it seemed to give reasonable numbers, but we moved on with a second design. In order to try to improve the design, we tried to get a little bit more creative and see what happened. We saw that there's very big stress concentrations on some places, so we added more trusses. Design 3, you see the effects of it. Still, the very first design was getting better results, so we decided to go back to the fundamentals on Design 4. Design 4 here, we saw a huge improvement. However, there was still room for a little bit more improvement, and hence Design 5. Design 5 was by far one of the best ones, and a little bit more of that will happen in we'll discuss that a little bit more in the results and discussions. So boundary conditions. Thermal boundary conditions for a radiation analysis was governed by the Boltzmann law. The equation here was used, MATLAB was used to crunch numbers, steady state was assumed, and both cold and hot scenarios values were extracted. Two main radiations were considered, the sun's and the Earth's. A cold case scenario was assumed when total eclipse deprived the structure from sun's radiation. A hot case scenario was used with an intensity of 114 watts per meter squared when the sun is closest at perihelion or during the summer. So both the sun and Earth were assumed to be perfect spheres and black bodies. All other forms of heat transfer and radiation are negligible at low Earth orbit. Thermal condition was added to replicate the temperature environment the structure would be subjected to. So all these numbers were verified by a published paper, Thermal Modeling of Nanosat, which is a thesis, and the sources are at the end of this presentation. Dynamic conditions. The projective values for both the thermal and the dynamic problem will be greater at steady state, meaning the peak of acceleration and the peak for thermal values will be higher when it's at steady state. So focus in the steady state solution will tell us if the structure will fail or where we can cut corners and maximize structure efficiency. Using the International Space Station as reference, volume per weight ratio can be deduced. And because we have the volume of the pod, with this we can guesstimate a good ballpark weight for the structure. Because the focus is on steady state mode, a static structure problem is used to simulate the forces acting on the structure at full speed. The induced centrifugal forces are exactly 9.81 meters per second squared, and since the mass is known, so is the force. The force load is applied at the center of the mass of the pod. This is where the picture. A fixed support is added at the base of the structure to fully represent what is going on when the structure is accelerating the structure, which is here. Superimposed results. Thermal results are independent of the structure loading, therefore can be computed alongside static structure without any issues. So a safety factor of 1.5 will be employed, and a service life standard of 1.25 will also be used. This was taken from the NASA technical standard book. This leads us to meshing. A fine mesh and a default element size were used to find stress concentrations in the structure. Due to licensing problems, we could not refine the entire structure. Instead, we dissected the areas and refined them where we saw big stress concentrations. A particular property we sought after was strain. The structure did not fail after one load, it failed after several. So the less strain, the less risk of failure due to fatigue. So a mesh verification study was done using strain, and we ensured convergence on the first design and on the final design. So here we have a mesh comparison. On the very first design, which is this one, we have a default mesh, and on the second one we used a sphere of influence here. That was a big concentration of stress, and after this you can see how it refines the mesh, particularly in that area. So this is a structural error, and it tells us it's the same sphere of influence here, where the structural error tells us 0.1657. After the refinement, it drops all the way to 0.0014. So it's a significant improvement. So here we have a mesh verification study. So this is on the very first design, which we kind of used to make sure that our meshes were converging, and we kind of stuck to that method for all 5 designs. Here we have the number of elements increasing, and as it increases, we see a convergence around 0.006. On design 5, we see a similar trend. So we see on the final mesh with the most elements, it converges. Results. We're interested in evaluating the structural integrity of the structure. For this, we look at 6 key factors. The first one is equivalent elastic strain. High strain module helps us optimize the mesh and structures. The less strain, the higher the fatigue life. Total deformation. Total deformation makes deformation tangible to something to contrast to. It could tell us, if it deflected 1 meter, that seems like a lot. If it deflected 0.00 something meters, that's a lot, which this image shows us. Um, so equivalent stress, it's another tool that helps us figure out stress concentrations and where we could put extra structures. It helps us optimize here, and here we see the 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 model that we put more structures to diffuse that stress, and here we see the results, which actually did make a difference. So all of these contribute to fatigue, and fatigue it kept showing up. It kept being the most popular failure mode in all my designs. Um, so another thing we look at is safety factor. Safety factor needed to be a 1.5 or higher. That was a must. Fatigue, uh, the most popular mode of failure, something we really had to look at. And life, how many cycles, instead of looking at a normalized data, exactly how many cycles were shown. So now we're looking at results. So this is using the best possible mesh and how we led to the actual design. So this is a lot of simulations compiled into one table. Um, First we have design one, which with 4 supports, it gave us 182 cycles before it failed. The COD case scenario with 24 degrees gave us 3,902. We deemed it not acceptable. We moved on to design 2 with 3 supports. We ran a hot case scenario first. It loaded 37, so judging from the first design, obviously this would fail. We moved on to design 2, 3, 4, 5, all the way up to design 5, where we finally saw an acceptable um, cycle, and we decided that would be our design. So now that we have our geometry, we moved on to experimenting with different materials. First, we did a full run with structural steel, looked at the safety factor, the service life standard, then we moved on to titanium and magnesium, and then aluminum. Aluminum is 2219, I believe, is what they use at the International Space Station. We compared equivalent stresses, equivalent strain, total deformation. This was all a bunch of simulations compiled into one table again, and we prepped it for to analyze, and that's what we'll see next. So before we continue with the materials, I want to take a step back and look at the design. So the first designs failed utterly. We did not even put them in the table or anything. The magnitude at which I was straining the structure was far greater than what I anticipated. The designs seen on the table are after a few iterations. Design 4 and 5 is where the breakthrough happened, and a genuine direction as to how the final model should be started sprouting. 4 supports were decided on to ease on the loadings and increase our safety factor. So these were the 5 main designs that I ran a full analysis on. Design 2 and 3 are a little unique. I tried taking a different direction when I stuck back to the fundamentals. Design 4 and 5 are the ones that were the most effective. Design 5 being our final solution and what we see in the final design. So again, a full study was done with the structural steel. Partial analysis were conducted for other materials, titanium, aluminum, and magnesium alloy. Not all data was available for in-depth analysis for some of these materials. And again, some of the main indicators for fatigue failure were high strain, high stress concentrations in the model, but for properties, yield strength and fracture toughness were key. And that's something we were particularly interested in every design. A key thing we noticed from every design was that the fatigue uh, factor of it kept showing up as very little, and that's particularly at one point we stopped looking at strain and stress and kind of just focused on on the fatigue factor. Once the fatigue factor was solved, we went back, looked at the stress, make sure everything checked, and more often than not, it did. So everything collapsed to what we see here in this image. So the final design, the desired structure integrity was met in the final design with both desirable service life and a safety factor, meaning the pod can be overloaded without issues. There are obvious problems, however. The weight of the structure just in the beams is about 111 tons. That's about one-fourth of the entire ISS weight. So a better solution for materials is needs to be explored, and hence our recommendation. So once the design was chosen, a material optimization was attempted. Although most materials needed S&N curve to perform fatigue tests, a correlation can be extracted from the material's data. A trace study was conducted to recommend other materials. So on the left table, we see some of the analysis done for structural steel at 75 degrees, titanium, magnesium, and aluminum. These were done under 24 degrees. Unfortunately, the parameters for running it at 75 degrees were not there, so we could not test for that. However, we did get safety factors, total deformations equivalent to compare to with structural steel at 24 degrees. And with density on the right side, we have a density, yield strength, fracture toughness, and Young's modulus. So uh, yield strength and fracture toughness can tell us a little bit more about the fatigue life of the material, and that's something we focused on when doing our trait study. So this is the grading system I gave for this trait study. So we have steel, aluminum, titanium, magnesium. On the right side, I put the level of importance. So density, which correlates to weight, was very important, 40%. Together, yield strength and fracture toughness yield the other 40%. This is an indication for the fatigue life. Young's modulus and the safety factor are obviously two important things, but uh, not nearly as important these other three parameters. So these gradings were all based on the data sheet we saw. Um, so here, density magnesium was the lightest, so it scored a 4. 4 points. Aluminum, the second lightest, titanium, and steel. So the maximum possible points was 5 out of 5, and given the grading, uh, titanium came out to be the more viable option. Unfortunately, we couldn't do this with composites because it's a little bit more complex. So for this, the main objective, or whether the structure seemed to fail the most, was in the fatigue test. So an emphasis was placed on that particular category. The safety factor cannot be compromised either, so as long as that stays above 1.5, the material was able to be considered. So building the structure out of titanium would reduce the weight to 28 tons instead of 111, which is about one-fourth of structural steel. This is a big consideration factor as to why we should look into other materials. So the model shows under the same environment and the load that titanium will perform better in most categories. So with all this said, I guess the next step would be to test on titanium, get full SNN curves, and test that out. So as a conclusion, the design criteria were met. It was resistant to fatigue, service life, structurally sound, 1-point phase safety factor, and the designs were optimized to handle the most loads while not using as much material as possible. So although the categories seem to be met, one of the things that were not taken into too much consideration was weight due to the limited properties of the materials we had. We can only do a full analysis on structural steel. So, but with this, we can extract and and correlate mechanical properties and simulation behaviors to the other materials. And with this, we conclude that titanium should perform better under cyclic loadings and to be about one-fourth of the weight.